All right, so last couple of lectures, we took a look at two important concepts. One was linear least squares, okay, and one was logistic regression. So let me give you the fundamental idea in both of these concepts, and then we'll continue onwards to develop neural networks, which these two concepts will help us understand, why do we need neural networks, what's the limitation of these techniques, right? So if you recall, in the linear least squares the idea was that suppose we are given some data, okay, and we wanted to fit this data by a line. So if it's a straight line, we wanted to know, for example, y equal to ax plus b. Okay, so what is a, what is b? Because if you recall, b is the intercept, right? And a is the slope of the line, which best fits the data. So if you recall, the way we did it was we defined a loss function, which will be basically a of xi plus b minus yi squared. And if we are given n data points, this will be our error function of the loss function, right? Then by partial L over partial A, set it equal to 0, partial L over partial B, set it equal to 0. So then we can come up with a, once we do the partials, we can come up with a matrix equation. And if we solve the matrix equation, we will know what is the best model that will fit the given data, right? And remember, in this particular example of the linear least squares, a and b were our model parameters, right? If we wanted to fit it by a linear model, we will need two unknowns, in this example, a and b. What if we wanted to fit the data with some kind of a curve, like something like this, right? So then we can think of it, in that case, let's do this. The equation for this curve will be ax squared plus bx plus c, as an example, right? So then, how will we describe our loss? See, in the ideal case, the y value will be exactly, if a, b are given to us, and x is given to us, some x is given to us, the y will exactly be on the curve, right? But whenever we have data, there's always some noise. What if the actual data is over here, but not over here? So that's where we come up with the idea of the loss. So the loss in this case will be ax squared plus bx plus c minus y. And as you can see, if the point was exactly on the curve, what would this value be? 0. So our goal will be essentially to minimize this loss. And sometimes the data point may be given above the curve, sometimes it may be given below the curve. So once we take the square, as you can see, that takes out the positive or negative error out of it. So a popular loss function is always the error square. Okay, not always, but that's one of the popular functions. And so again, in this case, if our goal was to find the exact equation that fits this data the best way, what would we do? We'll do if this is L, right, L equal to loss, partial L over partial A, we'll set it to 0. Partial L over partial B, we'll set it to 0. Partial L over partial C, we'll set it to 0. Okay, So again, in this case, there will be 3 equations, 3 unknowns, and we can solve for A, B, and C. So the linear, once again, in this case, does not mean that the curve that we are fitting is a straight line. Linear basically means that the model parameters, in this example is ABC. Once you are doing the assignment, I call them beta 0, beta 1, beta 2, right? So the model parameters are just simple multiplications with the variables. If we had a loss function where, let's say, regardless we are using ABC or beta 0, beta 1, beta 2, if we had something like this beta 1, beta 2 x squared plus beta 0 x plus beta 1 cube, something like this. Can this be solved using this technique?
No.
No. So then it becomes a nonlinear estimation, and nonlinear estimation can only be solved using iterative techniques, and gradient descent is one of those popular iterative techniques, right? So anyway, to summarize, if you're given a simple curve fitting problem, okay, the simple curve fitting problem is also referred to as regression. So if you're given a simple regression problem, okay, meaning the model is not too complicated as a simple curve, then you can try the linear least square approach by taking the partial derivative, setting it to 0. But if the model becomes very complicated, for example, the data is something like this, sorry, can't go backwards. Okay, something like this, right? If this is how the data is, then obviously, it will not be a simple square. There may be a cube term to the power 4. So this is where, if it is more complex, as today I will show you, this is where neural networks will come in and will be able to do a really good job of regression, even if the curve looks pretty complicated. Okay. And then we'll develop the techniques such that, how do we, for example, if somebody gave you a curve like this, right? How would you know that you only have to go like ax cubed plus bx squared plus cx plus d? Or you have to go a to the x4 plus b to the x cubed, and so on. How would you know what's the highest power you will need? I mean, you can take a look at how many, minimas, maximas. Usually, cube will have 2 minimas to the power 4. Or you can try out fitting it with x cubed, fitting it with x4, and see which one does a better job. Okay, meaning whichever gives you the lowest loss will be the better model. Okay, so one of the things as we go to neural networks today, you will learn is, same thing, how many neurons should we use? Should we use 100 neurons, 50 neurons, 5,000 neurons to fit a particular data? Okay, again, we'll learn techniques so that we don't use too many neurons. If we use too many neurons, we refer to it like overfitting the model. If we use too few neurons, it will be underfitting. Anyway, okay, the other important concept that we learned first couple of lectures was the logistic regression. So even though, as I mentioned, the word regression appears over here, normally by regression we mean, curve fitting, right? Okay, but in the logistic regression, we don't mean curve fitting. We basically means classification. Or, as you guys saw last time, most of the time, binary classification. Where some data is given to us, we want to classify it as true or false, or somebody having the disease or not having the disease, right? So logistic regression is one of the techniques that we use for binary classification. So what does the problem look like? Before we go into more involved neural networks, let's try to understand. Okay, so suppose somebody gave you our data, and let's take a look at diabetes as an example. So we are given data for, let's say, 10,000 people. Okay, and for every person, we have features like height, weight, male, female, right, age, blood type, and so on. So let's say we have total of 20 features for each person, right? And for each person, we are given whether the person has diabetes or not, meaning, 0 means no diabetes, 1 means diabetes, right? Okay, so if we are given training data for 10,000 people, each person has 20 features. How will we set it up as a logistic regression problem? Okay, as you guys saw, what we'll do is we'll have to come up with a model, right? Our logistic regression model, if you recall, was something like this. Our hypothesis was beta 0 plus beta 1x or x of 1 plus beta 2x of 2 plus beta 20 x of 20. Okay. So what is x? What are beta 0, beta 1, beta 2, and all of these? Those are the model parameters, just like we had A, B, C in the case of the curve fitting example, right? And what is x1, x2 through x20?
The features.
Those are the features. So for everybody, we'll be given height. So x1 could be height. So if the height is, let's say, 65 inches, this number will be 65. If x2 could be the weight, if it is 150 pounds, x2 will be 150, right? Okay, so because in logistic regression, the goal is to turn it into a probability problem, right? So as you guys saw, what we further do is we pass it through a sigmoid. And remember the equation for sigmoid was 1 plus c to the minus x, right? And because if we plot this, this will always be something like between 0 and 1. Now, this will become a probability between 0 to 1. Okay, so after we have determined beta 0, beta 1, and beta 20, right? How will our logistic regression network look like? So take a look over here. This will be a sum. x0, x1, sorry, we started with x1, x2, x20, multiplied by beta 1, beta 2, beta 20, and this is beta 0 multiplied by 1, right? And then further, we pass it through a sigmoid. And this is our h of x. So this is what the logistic regression architecture looks like. So beta 1 times x1, beta times x2, x, right? Okay, so last time we discussed how can we turn it into a probability. So if you guys recall our loss function that we defined, because we wanted to maximize the probability, was something like this, hx of y of I, 1 minus h of x of 1 minus y of I, right? And so, we started out by first saying, what if we do this? If we have m training samples, like 10,000 training samples, h of x is the probability that It belongs to class 1. And this will be the probability that if somebody doesn't have diabetes as an example, right? Okay. But because probabilities are being multiplied, this could easily go to 0. So in logistic regression, so that we don't run into, where our computation becomes 0 and we cannot solve for anything, we often try log loss. So if we do the log loss, then this becomes, as you can see, yi log of h of x, and this will become I equal to 1 to m, and 1 minus yi, and log of 1 minus h of x. So anyway, after we have the log loss, the question is, see, this h of x contains the beta 0, beta 1, beta 2. So the question was, can we do the partial derivatives and set them 0 and solve it? And the answer was no, because this is a nonlinear problem. Okay, especially from the loss, the log is involved over here. So this only can be solved iteratively. So we will start out with initial value of beta 0, beta 1, and so on. And each time we will do beta 0 minus alpha, the learning rate, and partial L over partial beta 0, and so on. Beta 1 minus the learning rate, partial L over partial beta 0. And we just keep repeating this over and over. And this was what we call the gradient descent technique. Ultimately, we will have the beta 0, beta 1, and beta 2. How do we find partial L over beta 0? So in the last lecture, we went through the derivation, and the end answer was pretty neat. Okay, so to summarize, if somebody gave you a simple curve fitting type of problem, what technique will we use? Linear least squares. Okay, if somebody gave us a binary classification problem, no, for binary classification, logistic regression, this will not be an option. Because the purpose of this is curve fitting. The purpose of this is to make decisions, right? So logistic regression would be an option. Okay. However, if you take a look at this model over here, right? This is basically the equation of a plane in high dimensions. Okay, just like we have a straight line in 2 dimensions, it becomes a plane, like a flat sheet in 3 dimensions, and very similarly, so this is equation of a hyperplane. So if we had data, okay, let's say we had only 2 features. I cannot draw 20 dimensions. If we had 2 features, and suppose, okay, so what does logistic regression do? It tries to give us the optimal value of the parameters, right? Which, as you guys saw in the last lecture, is basically a straight lines, maybe somewhere over here, deciding whether somebody has diabetes or no diabetes, as an example. So some of the data, as you can see, could be outliers, meaning erroneous data. So that's okay, as long as majority of the data is correctly classified, right? Okay. Now here's the interesting part, so we'll continue from this part. The interesting part is, this is actually a single neuron. Okay? A neuron does the same thing. In the neuron, we have some features, we have some weights, we have what we call activation function, which could be a sigmoid. Okay, so now let me come to the next topic over here, which is neural networks. So we'll start with a single neuron, then 2-layer network, then 3-layer network, then we'll make it any size network, and gradually we'll deal with deep networks, and you'll see how they are used, how the mathematics is, and compared to these two techniques, are they better or are they the same? So let's try to answer that. Okay, so first let's start with a simple single neural network for classification. We can do regression also, so these can do both. They can either do classification or they can do regression, meaning curve fitting, both. So that's the nice thing about neural networks. Okay. So anyway, let's start out for classification, then later on I can also show you regression. Okay, and let's start with a single neuron. A single neuron, like I said earlier, will be, it has two parts inside it, very similar to logistic regression. We will have some input x1. It will be multiplied by some weight. So instead of the parameter beta, we call it weight over here. Weight. Okay, same way we will go x2, we'll multiply it by, right? And let's go xn and wn. So if the data has n features, n could be 20 or whatever, okay. Then lastly, we call this a bias. So exactly like logistic regression, let me call this sum. So the sum will be W1 times X1 plus W2 times X2 plus Wn times Xn. Okay, plus 1 times bias. Right? And then if you take a look, this is what we call an activation function. Okay, and then we call this the actual output or the computed output. So in my terminology, I'll use A for actual output. Okay. So again, just like diabetes, let's pretend we are given some data. And okay, so our goal is to find the decision boundary. So the decision boundary could be linear, could be nonlinear, so that we can separate one class from another. So anyway, a popular choice for the activation function is the sigmoid. Later on, we'll take a look at other activation functions. So this will be e.g. sigmoid. Okay. So now, given some data, right? So we may be given 20 features for example, this X data. So pretend n is 20, right? In the beginning, all these weights will be randomly initialized, the biases will be randomly initialized. So our first goal is, through the training data, let's find out what are the optimal parameters which create a nice distinction between the two classes. Okay, so goal is determine weights and biases that optimally describe the boundary between classes. In our case, let's start out with an easy case. It's a two-class problem, right? Okay, so let's pick one data point. For example, this X over here, right? Okay, suppose it has 20 features. So somebody will give us height, weight, whatever, right? 20 numbers. In the beginning, these are randomly initialized, so we multiply them, we find the sum. So this is very easy to calculate, as you can see. Now we will pass it through a sigmoid, which is 1 over 1 plus e to the minus s over here, as you can see, e to the minus s. S is the input to the sigmoid, so this will do the sigmoid of that. So the expression for A, as you can see, will be something like this, right? Okay, so the question is, in the beginning, these weights are randomly initialized. How can we learn from the known data and keep going back and keep adjusting these weights, okay? And again, as you will see, during the training, we'll use the gradient descent algorithm, okay? In the gradient descent algorithm, each time as we go back, we'll adjust these weights. How will we adjust these weights? For example, W1 will become W1 minus some learning rate alpha, which could be 0.1 times partial loss over partial W1. W2 will become W2 minus alpha partial L over partial W2. Wn will become Wn minus alpha partial L over partial Wn. And similarly, B will become B minus alpha partial L over partial B. Okay, so we basically will keep repeating this over and over again until it has properly learned from the data, and then we'll fix the weights. After the training, weights and biases will be fixed. Now, for any unknown data, somebody feeds us the data for this point. And our goal is to find out, does this person have diabetes or not? As you can see, now will be multiplied by this. Then it will be passed through the activation. Suppose the output comes out to be 0.87. What will that indicate?
It has a 0.87% of being
So the person has diabetes, right? So, but on the other hand, if this turns out to be a very low number, then nothing, right? Okay, so our goal is to determine weights and biases, right? Determine weights and biases. Okay, as you can see in the gradient descent, we need these partials. If we can compute these partials, then it will be an easy problem, right? Okay, so let me show you how we will do that. Okay, so think of it this way. First, we have to define the loss function. Okay, the loss function will have two inputs, the actual output being produced and so this is the expected output. Okay, and obviously as this keeps getting trained, what do we want the actual and expected to be close to each other or far away from each other? Close to each other. So now we can define a loss. Okay. So easy way to define the loss is, let's take a look at a square of the difference between these two. So for example, loss could be AI minus YI squared as an example. Right? Okay, so now from this picture, our goal is to determine partial L over partial W1, partial L over partial W2, right? So partial L over partial W1 as an example, right? Okay, so now let me show you a general concept first. So forget the neural networks for a minute. Suppose you're given a complicated system. So this produces some out, let's say O1, which becomes the input over here. Let's say this produces an output O2. produces an output O3. Suppose then it goes through the loss. And this is some output A, and this is some L. Okay, so if we have pretty complicated, we go from one to another, to another, to another path over here, right? Easy way to determine in this diagram, partial L over partial W1 will be, what we do is, we start backwards. So what is the input over here? A. So if we can start by partial L over partial A, right? Then what's the previous input or the to this one?
O3.
O3. So if we do partial A over partial O3, right? Then, because our goal is to find this, right? And so now we will go backwards over here. So output is O3, input is O1. So we will do partial O3 over partial O1. Okay, and let's pretend in this particular example, O1 is x1 times W1 squared. Let me just arbitrarily pick that the way this box is working is taking the square of this. Okay? So as you can see, our next goal is what? Partial O1 over partial W1, right? See, if you go over here, you'll see A cancels, right? O3 cancels, O1 cancels. What are we left with? Partial L over partial W1. Okay. So if we can individually compute this, individually compute this, individually compute this, individually compute this, for example, what will be in this case if O1 is x1 times W1 squared? What will be partial O1 over partial W1?
2x1
2x1 W1, right? Okay. So anyway, what if there was no square over here?
x1.
So it will be simply 2x1, right?
If it is not square, then it's x1.
Oh, sorry, no 2 over here, just x1.
Yes.
Okay. Okay, so anyway, coming back over here, now how will we find partial L over partial W1? Okay, let's write the whole chain in this picture until we get over here. Okay, so this will be partial L over partial AI, correct? From here to here. From here to here. Partial AI over partial S, correct? And then partial S over partial W1. Okay, now if you can tell me each part over here. So again, see AI cancels, SS cancels, partial L over partial W1. Okay, what will be partial L over partial AI? So take the partial with respect to AI. So wouldn't it be 2 AI minus YI times